In the previous session, we looked at the RCNN algorithm, which happens to be a multi-stage object detection algorithm. We also saw its derivatives like the fast and the faster RCNN. In this session, we are going to dive deep into the YOLO algorithm, which is a single-stage object detection algorithm. YOLO actually stands for you only look once. Just as the name suggests, instead of going through, say, a selective search or a feature proposal network, and then some pooling layer, and then getting some feature vector, and then doing classification, here we are just going to pass this or combine this into one network. So we combine this into this YOLO model right here, where we have our input image, which is resized and passed. We have the convolutional neural network. This is actually the YOLO network, and our output goes through a non-max suppression algorithm. Don't forget to subscribe and hit that notification button so you never miss amazing content like this. Now, the first thing we'll look at is this convolutional network. And here, unlike with the RCNNs, where when we have, say, this input here, this is actually our input now. This 448 by 448 by 3 input image. So we have this input image, and if we're in the case of RCNN, we would select the regions of interest, and then for each region of interest, for example, this one, we are going to pass it through a convolutional block, and then the pooling layer, and then feature extractor, and then classification. But here we do not have to go through each and every region of interest, or we do not have to slide through all our image. All we need to do is just pass this image, hence the term YOLO. You only look once. So you only the full network only looks at this image just once, unlike with the previous methods. And so here we have this input image, which is passed into this network. Recall the filters we had seen already. We have this filters right here, whose role is to obviously extract useful information from this input image. So we stack this different convolutional layers. You see conv layer, max pool layer, conv layer, max pool layer, and so on and so forth, right up to this point where now we have the fully connected layer. So you have a connected layer and a connected layer, and then we have this output. Now the way that we design this output is such that the output of a given input like this one is broken up into several grid cells. To explain this, we'll suppose that we're dealing with grid cell size of 3. So when we have an image, we're going to break this up into 3 by 3 cells. And then if the center of a given object is found in a given grid cell, like in this case, if we take this one, the center of this object is around, let's say the center is here. And then the center of this other object, let's say it's around here. Okay, so we have these 2 cells here, which contain the centers of the 2 different objects we have in this image. If we want to consider this bangle as an object, then we could also have this too. Anyway, we have that set, and then the way we are going to construct this output, yeah, you notice here we have 7 by 7. Now, since we having 3 by 3 grid cells, we'll replace the 7 and by 3. So we have 3 by 3 for the purpose of simplicity, so you could see it clearly. Anyways, in practice, it could be 7 by 7, 11 by 11, 19 by 19. So let's have it at 3 by 3, and then we'll understand why we need this third dimension right here. Getting back to our grid cells, for this first cell right here, for cell 1, what we're gonna have is no object. So we're gonna encode this as no object. And for this cell, we're gonna have, let's focus on just this one cell. So we pick out this 1, 2, 3, 4. So we'll look at cell 1, then we'll leave this ones out, and then we'll look at cell 4. Now the reason why we're looking at this and this is because here there is an object, and here there is no object. So when there is no object, we encode this as 0. And then since there is this encoded as 0, we have different possibilities. So we're supposing that we have say 20 classes. That is, we have 20 different objects we're trying to detect. Let's even keep it simple by saying we want to detect just 4 different objects. So here we have this 4 possibilities: a person, a car, bracelet, or a cup. So this is what our object detection algorithm will be trying to detect. And then from here, we're going to include a case where we have no object. So we're going to have, in the case where it's 0, so we have here 0, we have 0. So for the person is 0, for the car is 0, for the bracelet we have 0, for the cup we have 0. And since we have in this cell no person, car, bracelet, or cup, we have this 0 for person, 0 for car, 0 for bracelet, and 0 for cup. So that's how we encode this. And then for the bounding boxes, or for the bounding box, the value we'll be having here wouldn't really matter since we don't actually have any object in that cell. So we have these 4 possibilities: x mean, we have here x mean, y mean, x max, and y max. To understand the way we write in this, you could consider that if you have, say, this bounding box right here surrounding this person like this, then the x mean is this distance from, like, this is the origin here. We're supposing that this is the origin, the top left corner. So here's our origin. The x mean is this distance from this origin, the horizontal distance right up to this first edge we have here. And then the y mean is this vertical distance from this origin down to this edge. So we to get this x mean, we move this direction. To get the y mean, we move downward. So that's how we get x mean, y mean. And then to get x max, we going to go through the same process, but we'll go into this edge. So this is our x max, y max, or this is our point for the max, and this is our point for the mean. So mean, again, we go this way and downward, and then for the max we go this way right up to this point. So we this distance is our x max, and then this distance downward is our y max. So that's how we understand this, and that's how this is encoded right here. Now we've understood how we're going to encode this grid cell right here. This first grid cell is going to be similar for this and this, because they actually know, we consider that there's no object here since the center of this object is found in this grid cell instead. Now we move to this fourth cell where we have this person. Now where we have this person, we're going to encode this differently. We start with the fact that instead of 0 we have 1 to say that there's an object, and then for the next 4 we have 4 different possibilities. Now since it's a person, we have a 1, and then the rest zeros. So there's no car, no bracelet, and no cup. And then for the bounding boxes, we're gonna now have the x max. That's, we're gonna actually, like, from here's what we have. Our x mean, y mean is the origin, so we have here 0, 0. So here's our x mean, and here's our y mean. So here we have here 0 for x mean, and then the next one will be a 0. And then for the x max, we just go from this, we go in this direction, horizontal direction, to the right, and then up to this point. So yeah, if we suppose that this is, for example, a 200 by 200 pixel image, or let's say 448 by 448, and that from here to here is 400, then here we will have here x max 400. And then the y max is this distance from here going downward. And since we've agreed that this is 448 by 448, then the distance from here to this bottom here is 448. So this to this 448, here we have 448. But actually in the paper, it's not exactly these values we pass in. So what's going to be passed in is a fraction, which is essentially these values which have been normalized. So to normalize this, we could decide to say, okay, we're going to take this 400 and divide it by the height and the width, or rather divide this by the width of the image. So 400 divided by 448, we have the value, we put here, and then 448 divided by 448, we take the value and we put here. But anyways, we're not going to get into those details now. All we have to understand is the logic behind the way YOLO outputs have been created. And from here, it's clear that if you have many more objects or many different types of objects you want to detect, then the length of this third dimension is going to be even more than what we have now. Like now we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So the length of this third dimension is 9. Unlike here where we have 30, here is 7 by 7, here we've taken 3 by 3. So that's how this is encoded in the YOLO algorithm. Then the other part we're talking about was the non-max suppression. So we've looked at how the convolutional network is being designed, and then now the last part is the non-max suppression. So before going to the non-max suppression, we are going to recall that when we have this model, like when we have this kind of model and then we have our data, by having our data means we have our input image and we have the encoding of that input image in this form right here. So once we take our input image and we encode it like this, we now train this model. So this model goes through a training process such that this weights, the filter values are being updated. So once these filter values are updated, it makes our model now becomes intelligent, in the sense that when you pass in an image, this image is going to generate an output such that we are able to detect at each and every position whether there's an object or not. And in the case where there's an object, we're able to detect the class of that object and also the bounding box surrounding that object. But the issue is that once we do this prediction, that's once we have this output, that's after training and then doing the predictions, we generally do not have exactly the kind of outputs we want to have when dealing with a YOLO. So that's why we make use of the non-max suppression algorithm. To understand how the non-max suppression algorithm works, let's consider that we are having an input which is being passed here. So we have this input which is passed into our neural network, and then we have an output in which, for example, where we want to detect this person right here, we have this bounding box. Now let's make this simpler. Let's suppose we're detecting just the face. So let's take this off and detect just the face. So we're detecting just the face. We're supposing we're detecting just the face. So we have this face right here, this detection for the face, and then we have this other detection still for the face. You can see clearly already that this isn't the best bounding box for this face. And then we have maybe let's say we have something like this again for the face. So we may have this too for the face, and then we may have, let's say, this for the face. Anyway, let's keep this simple. Let's take this one off. So we have this for our face. We have this first here. So we have this one, this first detection, this first bounding box. Let's suppose that the score or the probability of this being an object is 0.9 here, and then for this one we have a probability of say 0.3, and then this one we have a probability of say 0.6. Now the way the non-max suppression algorithm works is that we start by prioritizing these bounding boxes with a high probability score. So we prioritize this, so we take this first and then this one before this one. And so since these three boxes are all detecting the same face, what we want to do is to eliminate the boxes which are making us have duplicate detections. And to do that, what this does is, as we said already, we go in order, or we go in descending order. So we start with this first one and we let this here, but from the next one we're going to eliminate this bounding box, simply because we already have this bounding box here with a higher probability scores compared to the 0.6. So this one is eliminated already. Now we get to the 0.3, we still eliminate it because obviously it's far less than the 0.9 value we have here. And so after we pass our image and we have this kind of output, so if we have this kind of output, the role of the non-max suppression algorithm now is to ensure that we do not have duplicate detections. Now one question you may ask yourself is, what if, for example, we had a bounding box for this bangle? Let's take this 0.6 off here. So we have this, and then we have this detection for the bangle, and let's say it happens to go through like this. So it doesn't detect quite well. It gets into some parts of the face. Now we have a value here, or we have probably this score of say 0.7. So this is a detection for the bangle. Now if we were to go through what we just said, we are going to have, okay, this is 0.6, so let's put that back. We're going to have this one taken off, so we'll take this one off, take this one off, take this one off, and then also take this one off. So we'll also do this. But the problem here is this here, this bounding box we had here wasn't detecting this face, and so it doesn't make sense to remove this bounding box. And so if we proceed this way, we would have this bounding box which has been deleted, and we have only this prediction, whereas initially we had this bounding box for this bangle right here. But actually, since this bangle and this face don't belong to the same class, this bangle isn't going to be removed, or rather this bounding box surrounding this bangle isn't going to be removed. Now let's take this off and take another example. So what if, let's maintain, this is still 0.9, let's put it out here, 0.9, and then we say we have some bounding box here. Let's take this off. We have this other bounding box for a face, or still representing the face. We have something like this, and then we have this other bounding box still representing this other face. So we have this bounding box for this other face right here. Now it's clear that this bounding box is for this face, while these two are for this face. And what we want to have is a situation where this bounding box is taken off and we're left with just this one and this one. But unlike the situation with the bangle where the classes were different, where we could let this one stay because the class here is different from the class here, here we have the same class. And to solve this problem where we may be tempted to delete this one, so we're supposing that this has a threshold of say 0.85, or rather a score of 0.85, and then this one, let's say 0.7. So here we have 0.7. So as we're saying, we may be tempted to delete this bounding box right here simply because its score is less than that of this bounding box of score 0.9, whereas that shouldn't be the case because this bounding box is for a different face, while this bounding box is for this other face. And so to solve this problem, we'll make use of a concept known as the IOU. So we'll have this IOU, which actually means intersection over union. The role of the IOU is essentially to help us differentiate between bounding boxes which are predicting different classes, and that's by making use of the closeness of these bounding boxes. So that said, if we have this bounding box and we have this other bounding box here, so let's say this is case A, we could also have this other case B. We have this here, and then we have this other bounding box. Should be straight. We have this other bounding box, case B. We should note that the IOU score in case A will be greater than the IOU score in case B. So the IOU A will be greater than the IOU B. And we could see that clearly because these two bounding boxes are closer to each other as compared to this other two. Now to compute this, what we do is we take the intersection of the two, so this portion, and divide it by the union. The union is the total area, so it's this area here, all this here, which also obviously the intersection is part of the union. So we have this, all this is a union. Let's get back so you see only the intersection. So we have that. Let's take this off and this off. So we have the intersection and then we have the union. We could use a different color for the union so you could see that clear. And that's it. So that's the union. That was the intersection and that's the union. So we take the intersection and then divide it by the union. So we compute intersection divided by the union. And so what this implies is that if we have these two bounding boxes here, let's say we have this bounding box and we have this bounding box which is let's say we have another bounding box which is almost the same as this, then the intersection and the union are almost the same. It means that if we divide this two, what we'll get here will be almost equal to 1. So generally we have an intersection of our union score which lies between 0 and 1. So it lies in this range, and when the the IOU score value is approaching 1, it means the two boxes are very close to each other. While when it's approaching 0, it clearly means that the two boxes don't even touch each other. So we'll have this kind of scenario where we have this box and this box which don't touch each other. They'll have an IOU of 0. So getting back here, we could see clearly that the IOU of this box, or the IOU between this box and this box, will be very small as compared to the IOU between this box and this box. And so the way the non-max suppression works is that even if these two have belong to the same class, we are only going to delete these boxes of lower probability if and only if the IOU between the two boxes is greater than a given threshold. So we would have an IOU threshold, which can be, say, for example, 0.5, and which gives us the permission to whether delete a box or not. So in this case, if we get back to the algorithm, let's take the razor tool. We have 0.9, we have here 0.7. The IOU score is greater than the threshold, so we take this off. We take this one off, and we're left with that. Now we look at this two. They belong to the same class, but the IOU score is below the IOU threshold, so we let this go. And so at the end, we still have our two faces which have been correctly detected. And this is exactly how the non-max suppression algorithm works. So we've now looked at the YOLO version 1. After the YOLO version 1, we had the YOLO version 2, YOLO 90, and now we're going to look at the YOLO version 3 entitled An Incremental Improvement. YOLO version 3 comes with modifications like the bounding box encoding, which also takes into consideration the fact that we are now using anchor boxes. Now, to understand the concept of anchor boxes, let's come back to this illustration we had seen before. So we had those different grid cells, and if we pick out this cell, for example, we have the object next score, whether it's 0 or 1, that's whether there's an object or not. And then we have this next 4 for the 4 different classes. We're supposing we're trying to detect 4 different classes of objects, and then this next 4 for the bounding boxes. Now with these bounding boxes, it turns out that instead of allowing the network to predict, for example, here that this object is this bounding box, or that this bounding box surrounds this object this way, we are going to use predefined bounding boxes. Now the notion of, or the idea of predefined bounding boxes comes from the fact that many times the objects we have to detect take up certain shapes. Like for example, you will have objects generally like this, or something like this, or something like this, square like, and yeah, so generally we'll have objects taking up this kind of shapes. So if you have something like this, see, it looks already like this. So instead of allowing the network predict all this or predict this directly, we are going to allow the network predict this based off a predefined box, hence the term anchor box. And this permitted the YOLO version 3 to come up with even better results. Nonetheless, this increases computational costs, and so a model like the YoloX, that's the YoloX version, is always anchor free. Nonetheless, this increases computational costs, so a model like the YoloX is built without the concept of anchor boxes. The YOLO version 3 also comes with a modified feature extractor. So the feature extractor used for YOLO version 1 is modified to increase the speed and even accuracy. And then we also introduce prediction at different scales. So like here, you'll notice that if we have this image, you have something like this. Let's consider these two figures right here. You'll see that at the scale 3 by 3, so we have this 3 by 3, would have something like this, and at the scale 8 by 8, we would have something like this. Now, the advantage of predicting at different scales is that when you have this kind of larger grid cells, they can focus on predicting larger objects in the image. Whereas when you have this kind of small grid cells, they focus on predicting smaller objects. So this scale right here will be better optimized to predict this bracelet here as compared to this one here. Whereas this one will be better at, or will do better at predicting this person here, which is a larger object. And thanks to modifications like this, the YOLO version 3 outperforms the YOLO version 1. Now that said, we've just completed the section on the YOLO algorithm. The next session we'll look at the YOLOX variant of this algorithm.